I want to be able to travel to places I cannot, like inside the sun and inside the Earth. We'll avoid using a simulation. In our simulation, let's create a magic device that is indestructible, can survive anywhere, and we'll place this device 1,000 miles under the Earth. What can it see? Well, nothing, because it's embedded in rock. So let's clear a space around this device. We can do this because it's a simulation. Now the device can look at the rock. I think it would be fun if this device has the ability to manipulate things, modify its environment. Like it could put coal on a table and watch it turn to diamond. So this space should be pressurized. But pressurized with what? This video is about my quest to find a substance we could use to pressurize the space around our magical indestructible avatar device. The rules are, and we must have rules, we have a magical human-shaped indestructible observer. It can move around and survive arbitrary pressures and temperatures. Everything else does need to obey the rules of physics.
There are papers that use seismic measurements to determine the conditions at various depths.
The Preliminary Earth Reference Model, or PREM, provides tables of pressure at different depths. Let's put this data onto a graph. I'll put depth in miles on the x-axis and pressure in gigapascals on the y-axis.
As we move from the surface of the Earth on the left towards the center on the right, the pressure increases.
Let's add some meaning to these numbers. 1,000 miles is the distance between New York City and Miami. 4,000 miles is the distance between New York City and Paris. As far as pressure, 100 kilopascals is normal air pressure. 1,000 kilopascals or 1 megapascal is the pressure of a high-pressure road bike tire. It's also the pressure of a 120-pound person who steps on your thumb. For obvious reasons, we can't experience pressures much greater than this, and it's hard to see such pressures either. 10 megapascals is a hydraulic press. 100 megapascals is the bottom of the Mariana Trench. 1,000 megapascals or 1 gigapascal is the bursting pressure of an artillery shell. 10 gigapascals is the initial pressure of our 1 megaton nuclear warhead. 100 kilopascals normal air pressure, 1 megapascal a bike tire, 10 megapascal hydraulic press, 100 megapascals Mariana Trench, 1 gigapascal artillery shell, and 10 gigapascal a 1 megaton nuclear warhead. Now going back to our graph of pressure against depth, if I draw a line at 1,000 miles, we can see the pressure is around 70 gigapascals, 7 times more than a 1 megaton nuclear explosion. So that's going to be challenging. So that's pressure. Now let's look at temperature. The paper, A Revised Adiabatic Temperature Profile for the Mantle, gives temperatures down to 1,700 miles. I'll also add in some data for deeper in the Earth from melting temperature of the Earth's mantle and core and models of large-scale viscous flow in the Earth's mantle. On this graph, the x-axis is depth into the Earth and the y-axis is temperature. As we go deeper into the Earth, the temperature increases. This first flat section is the mantle. The mantle flows somewhat, which keeps the temperature fairly constant. This second flattish section is the outer core, which is molten and also fairly constant in temperature. The core is some kind of iron-rich alloy. At the boundary between these layers, there's a big temperature jump, and similarly near the surface of the Earth. Let's assign some meanings to these temperatures. 20 Celsius is room temperature. 100 Celsius the boiling point of water. 200 Celsius is baking cookies. 300 Celsius is a soldering iron. 500 Celsius is the surface of Venus. 1000 Celsius is lava. 1400 Celsius is the melting point of steel. 1800 Celsius is the temperature of space shuttle re-entry. So going back to our graph of temperature against depth under the ground, if I draw a line at 1000 miles, we can see the temperature is around 2000 Celsius, above the temperature of space shuttle re-entry. So yeah, temperature sounds pretty challenging too. Now, one good thing is that temperature and pressure are kind of opposite. High temperature makes things melt and boil. High pressure makes things freeze, so they might cancel each other out. Probably still lethal to humans though. Let's start with silica. Silica is quartz, which is what sand is mostly made of. Sand is solid at room temperature and pressure. TKOR has a video where they melt sand. At room pressure, you can melt sand at 1700 Celsius, but what about at 70 gigapascals, a million atmospheres? The paper Melting Behavior of Silicon Dioxide has a table of melting points all the way up to 120 gigapascals, which is amazing. They use something called a diamond anvil cell. A diamond anvil cell uses two tiny diamonds to generate pressures of hundreds of gigapascals. This lets us reproduce the conditions found thousands of miles deep into the Earth. We can take the data from Andro et al. And plot a phase diagram. Pressure is towards the right in gigapascals and temperature is upwards. If we pick a pressure, we can plot the melting point of silica at that pressure. So here we have room pressure and the melting point is 1700 Celsius. As we increase the pressure, the melting point of silica increases. This makes sense because the pressure squeezes the molecules together. At temperatures below the melting point, silica is solid like sand. At temperatures above the melting point, silica is liquid like magma. We are at 70 gigapascals and 2000 Celsius. We can see that silica will clearly be solid at these conditions. Let's check carbon dioxide next. CO2 can exist in a supercritical state. Supercritical fluids, or SCFs for short, form under high pressure and high temperature. If we start with a gas and add pressure, we get liquid. If we add temperature, we still get gas. If we add both temperature and pressure, then we get SCF. SCFs fill the available space like a gas, but are dense and can dissolve things like a liquid. The atmosphere on Venus is supercritical carbon dioxide. The surface of Venus is 9 megapascals and 460 Celsius. Together this is high enough for carbon dioxide to be in a supercritical state. We can see that the Venus atmosphere is maybe a little yellow, but clearly transparent. But will CO2 actually be SCF at 1000 miles, or will the high pressure cause it to freeze? Even when a material is above the critical point, it can still freeze solid if the pressure is high enough. The paper CO2 in the mantle, Melting and Solid Phase Boundaries provides data on melting points of carbon dioxide at high pressure. They're using molecular dynamics simulations. Here's the melting curve for carbon dioxide. Below the curve is solid as before, and above is fluid. We're clearly still below the curve, so carbon dioxide will be solid too, frozen by the tremendous pressure. Let's check water next. Now water is a liquid at room temperature and pressure, whereas carbon dioxide is a gas. But water is an anomaly. Hydrogen bonding between the water molecules makes water behave very oddly, so let's just check. So here's the melting curve for water. It actually goes right through us, so it's right on the edge. It's too close to cool really. We could use a heater in our lab and the water would be fluid. Of course, if the heater ever breaks, our lab might literally freeze. But actually I discovered whilst I was reading around a rather more serious issue. There's something called supercritical water oxidation. It turns out that supercritical water is basically liquid fire. It can oxidize anything. At the start of this video, we talked about putting coal on a table and watching it turn to diamond. Well, if we fill our lab with supercritical water, the supercritical water will destroy our coal, oxidize it, burn it. So we'll have to think of something else. Let's have a look at noble gases next. So noble gases don't really react with stuff. That sounds a lot better than using liquid fire. Let's check xenon first. Here's the melting curve for xenon. Oh, okay, no go. Alright, let's check argon. Oh, okay, so argon will be solid too. 70 gigapascals freezes everything. Here's the periodic table of elements, and here's the noble gases. Argon has a lower melting point than xenon, and argon also has a lower atomic number than xenon. The atomic number relates to the weight of an atom, and it makes sense that lighter elements will freeze less easily, because the atoms might move around more for the same energy. What if we chose an even lighter noble gas, one with a lower atomic number? Before argon, we also have neon and helium. So let's try. Here's the melting curve of neon. So we're pretty close. We could use a heater. And here's the melting curve for helium. Alright, so it passes well below us. Its melting point at 70 gigapascals is around 600 Celsius, so helium is clearly going to be a fluid. If we pressurize our lab with helium, we'll be able to move around inside of it. We can do experiments. In future videos, I want to think about how we could actually make such an avatar. Like, is that possible? Anyway, if you liked this video and you want me to make similar videos, please encourage me with a thumbs up.